Okay, so we've talked in geochemistry, we've talked about the composition of the Earth and the origin of the Earth and things like that. What we haven't talked about is what geochemistry can tell us about the present state of the mantle. So I thought I'd do just a very quick review of this. And I'm going to focus on radiogenic isotope geochemistry, rather than the trace I emphasized before. So, and again, the red or the radioactive elements, radiogenic, those produce the whites or the grays or the radioactive ones. I'm going to focus just on three systems: samarium decaying to neodymium, that's about 100 billion year half-life, rubidium decaying to strontium, about a 40 million year half-life, and uranium, which decays through a series of intermediate daughters to lead, two isotopes, one of which has a 4.5 billion year half-life and the other about a 700 million year half-life. So here's the basic business with isotope geochemistry. Here's the equation of interest for the rubidium-strontium system. It says, I always liked this quote from this paper by Paul Gast in 1960, which was probably the very first paper in isotope geochemistry. He was the first one to use radioactive and radiogenic isotopes to try to understand something about the evolution of the Earth rather than just dating rocks. Up to that, almost everything had been focused on dating. And he explains this equation this way. He says in a given chemical system, the isotopic abundance of strontium-87 is determined by four parameters. The isotopic abundance at a given initial time, which is this term, the rubidium-strontium ratio of the system, which is that term, the decay constant of rubidium-87, which we know fairly well from physics, although decay constants are occasionally revised. For example, the samarium-146, that short-lived extinct, has been revised from 100 million years to 68, and there's minor revisions of others, but mostly we know these. And the time elapsed since the initial time. He goes on to say the isotopic composition of a particular sample of strontium, whose history may or may not be known, may be the result of time spent in a number of such systems or environments. In any case, the isotopic composition is the time-integrated, and this is the key term, time-integrated result of rubidium-strontium ratios in all past environments. So, in other words, the strontium-87-86 ratio tells us about the history of the rubidium-strontium ratio. These are two incompatible elements, but rubidium being significantly more incompatible than strontium. Goes on to say local differences in rubidium-strontium will in time result in local differences in the abundance of strontium-87. Mixing of materials during processes will tend to homogenize these local variations. So when the mantle melts, there might be heterogeneity within the mantle, and that will be mixed into the melt, and we can only know about the bulk of whatever that melt sampling, for example. But no other processes affect these radiogenic isotope ratios. Once homogenization occurs, the isotopic composition is not further affected by these processes.
I just want to point out that the fundamental difference between most information that comes from geophysics versus that from geochemistry is that geochemistry is always a time-integrated signal, whereas in geophysics it's commonly the present Earth only. And that's why we have difficulties communicating with each other.
Sometimes. Okay.
Another question. But you are assuming homogenization. Actually, in many cases, geological processes will lead to the distribution, which is isotope dependent, or at least chain of decay dependent. Can we go beyond homogenization assumption?
Okay, well, advection and diffusion are fairly effective in the liquid phase and homogenizing. Okay, so this is the point. Once you make a magma, the likelihood is things will be homogenized. Right. Now, once the magma rises into the crust, it begins to crystallize. It dehomogenizes in a sense. But that crystallization process does not affect these isotope ratios. It does affect these trace element ratios. And that's the value of it. It's a true recorder of whatever the melt is sampling. We don't necessarily always know what it's sampling, but as it said, once homogenization occurs, nothing else affects it. Okay, so here's the oceanic basalt data set in epsilon, neodymium, and strontium. So these are two of the ratios. Epsilon neodymium, this is a shorthand way of denoting the isotope ratio. It's variations in parts in 10,000 from the chondritic ratio. Okay, so it's just a shorthand notation. This is the mid-ocean, where the mid-ocean ridges plot up here. All these red dots are mid-ocean ridge basalts. They scatter down here. There's even a few down here. But by and large, they're concentrated up here. The oceanic island basalts scatter into this area. And there is some overlap, but by and large, we're talking about two distinct populations. Now, there was a time when we thought that the bulk silicate Earth had an epsilon neodymium value of 0 here. I think this is very much come into doubt, and Bill McDonough would still claim it is, but some others think it's probably actually higher. My estimate of bulk silicate Earth would be here, and then from the correlation, we'd estimate a bulk silicate Earth, rubidium, strontium here. That's we don't have any other, well, we do have some other constraints on rubidium, strontium, but not from chondrites, because we know the Earth is way depleted in rubidium compared to chondrites. So the chondrites don't provide a good model for rubidium, strontium. So what this means is anything plotted up in this quadrant has experienced net incompatible element depletion, mid-ocean ridge basalt, so that's the characteristic, and things plotting in this quadrant have experienced net incompatible element enrichment. We can debate exactly where the bulk silicate Earth is. And notice I put in this gray area here that pretty much encompasses the range of possible values for bulk silicate Earth. Now going to lead isotope ratios. So this is 206 is the product of uranium-238 with a very long half-life. 207 is the product of decay of 235, most of which is now gone from the Earth. It's very nearly an extinct radionuclide. We see a very good correlation on this, which is actually largely to be expected. The other thing, I don't have time to go into the details, but lines on diagrams of these two isotopes have age significance because the ratio of these two isotopes of uranium doesn't change except over time due to radioactive decay. And in terms of where the bulk silicate Earth is, we can say it plots, depending on what we assume for at least the age of the silicate Earth, this might mean final core extraction because some lead might go in the core. It must lie somewhere between these two lines. I think most people would guess it's up here somewhere. Okay. Now, so I've shown you the lead isotopes and I've shown you neodymium and strontium. We can also look at neodymium versus strontium. Previously, we saw things correlate pretty well. When we look at lead and something else, usually the correlations break down. There is, however, some order in this chaos. Okay, and that's partly indicated by the color coding. Just note that for some of these islands, Hawaiian Islands, Iceland, Galapagos, there's so much data that it would just obscure everything, so I've just drawn fields. Okay, so we've known for quite some time that there is some order here. Some systematic variation allows us to divide oceanic island basalts and mid-ocean ridge basalts, and presumably the plumes that generate them into several varieties. I kind of like to think of them as, by an analogy to biology, I like to think of them as genera. And in these genera there are, in some cases, several species. But they break down as follows, and you'll hear geochemists throw these terms around. So that's why I wanted to introduce them. DMM, the depleted Moore mantle. That's the mantle source that gives rise to mid-ocean ridge basalt. EM1 type examples are Kerguelen, which is in the southern Indian Ocean, and Tristan da Cunha in the South Atlantic. EM2 type examples are Society and Samoa. And high mu, the term comes from the fact that those islands are characterized by particularly radiogenic lead, and geochemists speak for the uranium-lead ratio is mu, so high. If they have radiogenic lead, must have had high uranium-lead ratio or high mu. And then there's PRIMA, which is, I guess, a Zindler and Hart acronym for prevalent mantle. We'll look at these where they fall in a moment. Again, I showed you those. Other people have other people have identified sort of a component, if we want to call it that, that's interior to some of these arrays, or interior to the data set itself, and they've named it FOSO, C, FEM. I think these things, in some sense, are all referring to the same thing. We should also bear in mind that, yep, go ahead.
So EM1, EM2, you say type examples there. How many are there? Are there a lot of EM1 and EM2 hotspots?
There are others. We'll look at the data again. In terms of really extreme, some of these are probably the most extreme, although let's see, another good one that falls into here is Pitcairn. So particularly for these two, there are other sets that fall into there. Yeah. I'm going to go back to the data and we're going to look at it in a minute. Now, we're just looking at the isotope ratios. We're looking at the very small variations in the isotopic composition of trace elements. So I like to think of this in terms of flavors of ice cream. Okay, what we're looking at is the flavor, the orange or the lemon or the strawberry or the chocolate or whatever. We can't say very much about the milk or cream or sugar, okay, which is mostly peridotite, probably. So bear this in mind, that we're just looking at the flavors. Or if you will, we're looking at a tracer in a tank experiment, something like that. We can't, from the isotope ratios, it doesn't necessarily tell us anything about material properties or where these things are located. Now let's go back and look at the data again now that I've introduced the terms. And I've sort of color-coded things here. In the yellows and oranges are the high mu. Notice how they plot here, sort of off the main array. The EM2 spread out here. Matt Jackson really screwed things up by discovering some extremely radiogenic strontium in Samoa. And to actually plot that point, this would have to be such a small scale you wouldn't actually see what's going on. The EM1s, here's Tristan and Goff in the South Atlantic. This is Kerguelen and Hurd. I think I've got this. This is Pitcairn and Gambier in the Pacific. The Azores, Samoa and Society generally plot along here. The Azores, or at least one of the islands there, also plots along that trajectory. Very different trajectories there. Each of these things occupying a part of this diagram. And PRIMA, this is the prevalent mantle. It seems to be where everything's coming into, approximately, which is close to, but maybe not identical, to bulk silicate Earth. And then Iceland and certainly Galapagos seem more dominated by a more morb-like composition. Okay, so we still see some systematic variation here now if we just look at the lead isotope ratios. So here are the high, the EM1s again. Here are the EM2s. Notice how they sort of divide by lead, and they also tend to plot a little higher in the 207, 206 relative to 206, 204. And here's the high mu's running off like this. And again, PRIMA would be in here somewhere. And then if we go back and look at this diagram again, here's mid-ocean ridge basalt. So this is our, I haven't labeled it here, but this would be our DMM up here somewhere. The EM2s, or EM1s extending down to rather unradiogenic lead and very unradiogenic neodymium. EM2s not so unradiogenic neodymium and not so unradiogenic lead, and then the high mu's extending off to only moderate epsilon neodymiums, actually plotting perhaps in the depleted quadrant, but with extremely radiogenic lead. Where's Morb is the red dots again. Okay, so that's the mid-ocean ridge basalt field, and most of them are concentrated up here. They scatter about. One thing we find about Morb is as we approach some of these oceanic islands that lie along the ridges, the Morb takes on isotopic composition similar to the oceanic islands. It's first demonstrated by Hart and others in the case of Iceland, and then my thesis work in Azores, but it's also been shown in a number of other places. So we now interpret this as plume. Well, Schilling initially interpreted it in 1973 as plumes that then basically mix with or contaminate the lithosphere that's feeding mid-ocean ridges. Yes?
Why do some of these have such a large spread while others are more localized? Is there any reasoning to that, or is it just samples?
Why is there such a large okay, well, the short answer would be, I guess, I think in many cases, we're actually mixing something down here with something out here. I think most of these we can probably describe as mixing arrays. And where we have an extreme mixing array, we're going to get a very long field where the component is not so extreme in this particular view of isotopic space. We're going to get a much shorter field. Notice there's a lot of islands in here: Canaries, Cape Verdes, Amsterdam, Easter, Marion, Prince Edward, all sort of Mascarene Islands, Reunion, all sort of buried in here that actually don't really very much extend out into these regions. I think the principal interpretation of the arrays would be some kind of mixing. Let's see. Okay, so, well, in terms of, if there's some kind of mixing, what is it we're mixing? What are these EMs, the high mu's and prima and that sort of thing? Are they unique components contained in spatially distinct reservoirs somewhere in the mantle that then mix with each other? This is certainly probably true anyway of the depleted Morb mantle. It probably does largely occupy a region of the mantle, the upper mantle. Although actually we can identify Pacific, Atlantic, and Indian subspecies. Yeah.
So if you go back to that other chart, what would happen if you took and maybe indexed some of these samples by like when they were in place or timing?
Oh, okay. So these are all very, very young. I mean, everything here is all these analyses are probably of basalts that are less than a few million years old. In geologic time, this is zero time. Okay, the whole story of looking back in time is a different one that I don't have time to get into.
You have some of these things that were relatively in place and in the same time, but you have these large variations.
Yes, although
like they're the same spatial area and were in place at the same time. Why do they look so different?
Actually, I shouldn't. It's probably longer than particularly in some of these islands. We may be talking about as many as tens of millions of years. But the islands, these are not. They're not. Often they're island groups with distinct volcanoes, and very often the volcanoes. The distinction is between volcanoes. But in Kilauea, which has been erupting continuously since, 1982, 1983, we do see small variations in isotopic composition over time. But they're so small, wouldn't hardly show up on the scale I'm showing. So and the isotopic composition of magma feeding into a volcano, even on the timescale of decades, can change. But mostly, Yeah, but mostly we're looking at, mostly we're looking at a variety of different volcanoes. Samoa, there are a number of different islands and seamounts that have sampled, and those individual volcanoes tend to be a lot more homogeneous than this whole array. So we're looking at right. I mean, most of the variation is between volcanoes in an island chain. I guess that's the best way to explain it. Okay, so right now, this also might be true of prima and the high mu. At least it does seem to be something that mixes with almost everything else. And the high mu, I'm going to show you this in a while. It actually does seem to be quite a unique component. There seems to be only one high mu, but this is not true of the EM1 and the EM2. They're reservoirs in some sense that have evolved in a similar way, and need not. It doesn't mean that whatever is producing tristan is also producing curculan. It's just that those plumes contain material that's evolved in some similar way. You also have to be careful when geochemists talk about reservoirs. I'm using it in geochemical speak, and I'll give you an analogy. We can talk about a organic carbon reservoir in the crust and a carbonate reservoir in the crust. So, but same element, carbon, and they might actually spatially be in the same sediments, but we can distinguish, because they have different properties and react in different ways, we still can distinguish different reservoirs. And when I say a reservoir, I'm not necessarily implying anything spatial. Okay, so this is now a three-dimensional plot. And my colors and plotting symbols are somewhat limited in this software. Three-dimensional plot of the strontium 8786, the epsilon neodymium, and the lead 206-204 ratio. And now you can see how these arrays, the Samoan and the societies are actually distinct. They're not the same one. This is high mu. That does seem to be distinct. But here in the green and these blues, we actually have several distinct arrays. This would be the so-called EM1s that was supposed to continue playing. But at least for those two, we're not talking about something that's somewhere in the mantle that is always mixing into somewhere else. Again, I think we're talking about material that has evolved in a rather similar way, and it may be dispersed somehow in the mantle. Okay. So the big question, of course, is how have these genera evolved, and what does this tell us about the mantle? Okay, first for prima, I think there's some hint from the noble gas data. This is a paper by Klass and Goldstein, and they color-coded things based on the helium-3-4 ratio. Again, helium-4 is produced by alpha decay, but helium-3 isn't, and the Earth didn't start with very much helium-3, and it's losing it every day. So the highest 3-4 ratios are what we would think to be the most primitive mantle. That is least disturbed. If you melt the mantle, the helium leaves, okay? If you melt the mantle, you also degas it. So this is probably the least degassed mantle. And that more or less, this is the plot I showed you, the neodymium isotope ratio. This time it's written as the isotope ratio rather than epsilon. Let's see, epsilon 0 is right here. But you can see that this more or less corresponds with where prima was in those other diagrams. So it seems that prima may be the closest thing to an unprocessed primitive mantle that still exists on the Earth. Doesn't quite perfectly match what we expect primitive mantle or bulk silicated Earth to be, but in many ways it's close.
What are the open symbols in that?
Good question.
Oh, I see.
Samoa, yeah. Okay. I want to talk a little bit about stable isotope variations. Actually, just oxygen and sulfur, two of them. Unlike radiogenic isotope ratios, Stable isotope ratios do change as a result of chemical processes. First of all, we usually report them as per mil deviations from parts in 1,000, deviations from a standard, so notations like this, delta 018 SMO, which is standard mean ocean water. The ratios vary due to slight effects of nuclear mass on bond strength, reactivity, and diffusivity, and these effects decrease with the inverse square of temperature, and consequently, they're usually negligible at mantle temperatures. And so stable isotopes, at least the ones I'm going to be looking at, we can consider them to fractionate, or those ratios that change only at the surface of the Earth. So here's data from, again, Samoa, islands and seamounts. And we see a very nice correlation between delta 18 measured in olivine phenocryst and the strontium-87-86 ratio. So why do we have high strontium-87-86? Well, these elevated oxygen isotope ratios strongly suggest this is some sort of crustal component. And indeed, that's what we thought just based on the radiogenic isotopes. They're so extreme in Samoa, almost has to be crustal. So in addition to the radiogenic isotope evidence, stable isotopes and certain trace element ratios provide convincing evidence that the flavoring agent in our ice cream of the Samoan and Society plumes, the EM2s, is certainly continental crust. It's perhaps a little less strong for EM1 plumes, but I think they contain recycled crustal material as well, although perhaps more predominantly oceanic. I'm getting close to the end here. And here's, I'm going to steal Matt's thunder here. Okay, this was a really exciting discovery published a year ago. MIF sulfur in Mangaia. This is one of the Austral islands. Oh, I didn't tell you about high mu. It occurs only in 3 islands, 3 island groups. The Australs in the Pacific and St. Helena and Ascension in the South Atlantic. True high mu is really restricted. Okay, and Mangaia is that's the one with the most extreme. That island has the most extreme lead isotopic compositions. So within one of the olivines in the lava, they found a sulfide inclusion. And the sulfur isotope ratios, normally we would expect sulfur isotope ratios to, on this plot anyway, fractionate this way. That is, we would expect the delta 33S and the delta 34S to correlate. They don't. And this is called mass-independent fractionation, when we get the same amount of fractionation of 2 different isotopes. And it's a very rare phenomenon. And generally, so far, every time we've been able to explain it, it seems to involve photodissociation. In this case, and it does in fact occur in the modern stratosphere. And this shows sulfur isotope ratios. This is the extent of mass-independent fractionation on this axis. This uppercase cap del 33 sulfur. Everything after 2 billion years doesn't show this. But there's a signal of this mass-independent fractionation before about 2.3 billion years ago. Okay, well, that's just about the time we think the atmosphere became oxidizing. So the explanation is, before that, there was no oxygen, there was no ozone to filter out the ultraviolet light. It could photodissociate the sulfur in a way that led to this mass-independent fractionation. So there's a whole really interesting story there, but just what that means for us here, I think, is that in fact, this mass-independent fractionation means that this high mu also must contain a superficial component recycled back into the deep mantle. Okay, that's all I wanted to say. Any quick questions again on that? Yep, Michael.
Is the Earth well enough sampled now that you don't think we need to add any more species to this classification?
Well, that's a good question. I don't think we're going to find any more genera, and we've sampled almost every active intraoceanic volcano. So maybe there'll be some way to look at, I'm doing this myself, look at this data statistically and try to break it up. But I think, I would say, we haven't necessarily found the most extreme. values for any of these. Okay, so Matt's work in 2007, I mean, I worked on Samoa several times and found pretty high strontium isotope ratios, and then Matt did his thesis there and just was off the charts. So there are things to be discovered. I'm not sure it's going to be very, and it may well be a lot more extreme than what we've seen, and there might be things like this that are very revealing. But I think the spread in the isotopes is probably not going to change. Yeah.
I have a very related question. With regard to morb samples and measurements, so two-part one is, are those samples near the ridges, or do we have a sampling with time, like older morbs as well?
We do. And from the deep sea drilling project. So, we've got certainly things that are as old as the existing ocean floor out in the Pacific, 160, 180. That's pretty much the same. And then we try to sample ophiolites back in time and track the evolution of this depleted reservoir over time. And we can do that to some degree, but that's a whole different story. Be hard to get into.
Second part of the question is, spatially, are morbs spatially sampled well enough that we're confident are there places in the world that we should measure more, or do we have a pretty good?
Oh, I think the more extreme parts of the ridge system are still not well sampled. In the South Pacific and Southern Indian Ocean, places people don't really want to go to. It's still worth sampling more. I don't think it's going to change the data set terribly.
Does lithospheric contamination remain such an extreme problem that you can derive nothing out of continental flood basalt or flood basalt, period? Because the oceanic basalt suite is wonderful, but it's really sort of zits on the surface of the planet, whereas the continental flood basalts are really very profound events. And what's happening there?
To the degree that we strip out the lithosphere and continental contamination, it's not different, I think. Is that, although Matt, I think, was involved in some of that work. In the case of Baffin Island, which is probably the start of the Iceland plume, you find some even more, some of the most, and also on the Kola Peninsula in Russia, we found some of the most extreme helium. Okay, we might actually have found better evidence of a primitive mantle component in some of these flood basalts. But I was involved in this in Deccan, the Deccan reunion plume. We can trace that all the way back. We see a slow evolution of the plume over time, as we can in Hawaii when we look at the older and older islands. But there's nothing enormously revolutionary necessarily about it. Yes, Barbara?
So how does this classification relate to the one for trace elements? This classification and these different groups, how does that relate to the trace elements?
Okay, yeah, no way did I have time to go into that. But yes, we can see some systematic, and somebody's question pointed out when I was talking earlier on Monday about, or whenever it was, that Samoa looked really different in its spider diagram, and that's true. Okay, so we can see some differences that we can, in some cases, relate to parents and daughters in the trace element patterns, so yes, it's a lot harder because the trace elements, in fact, are also functions of extent of partial melting and to a lesser degree fractional crystallization. I should probably let Adam take over.